Let's start with the second talk of this afternoon. So it's my pleasure to introduce Hiroaki Nakamura from Okayama University. And the title of his talk is Arithmetic Invariants of Eisenstein type arising from fundamental groups of one punctured elliptic curves.
Thank you very much. First of all, I thank the organizers very much. So today I want to talk about such invariants. Mainly, it represents the information of monodromy representation on the meta-abelian quotient of fundamental group. It's actually the elliptic analog of Ihara's power series, universal power series for Jacobi sums arising from a fundamental group of P1 minus 3 points. And once punctured elliptic curve has a same homotopy type with P1 minus 3 points over algebraically closed field. But over arithmetic field, the structure is quite different. So we also need somehow to essentially different constructions for compared to Ihara's original case. My talk plan today is first I want to maybe very slowly introduction and motivation present is better, and then after that I made exhibition of my approach today. Then after that, I little bit changing. I will be a little bit changing the topic, Abelian geometry or GT theory, Grothendieck Teichmüller theory on moduli space of elliptic curves and over universal curves over it. Then finally, I would like to show some Dedekind sum formula. And one of the goals of my talk today is somehow presenting a device producing such a matrix infinitely many ways. This matrix is every time you are given a 2 by 2 matrix from SL to Z, you can produce such 3 matrices. One matrix and the first and second matrix has big denominators, usually with rational number entries. But after that, some magic, you can always get integer values, valued matrix. So from here, maybe elementary arithmetic study could be enjoyed afterwards. But today I have to stop here. Yeah. Okay. So first, introduction. So I want to begin with Weierstrass equations of elliptic curve. And I'm working over a field and characteristic equal 0. Then we have a natural standard first differential form here. Then the condition that this has smooth is the discriminant of this thing. I just delta. It is well-known formula is invertible in K. Then first we want to formulate Galois representation in this fundamental group. So I take standard Weierstrass tangential base point which is valued at with power series of k bar in variable t, and t is taken as a such function giving the local coordinates of the missing point at infinity. Then, so this algebraically closed field gives rise to generic geometric point on elliptic curve minus 1 point infinity. This is infinity in this equation. Then it gives rise the splitting exact sequence of a profinite fundamental group. Pi1 geometric of B minus O and arithmetic fundamental group and absolute Galois group of K. And this tangential base point has a natural action of Galois group on the coefficient-wise action on this omega, so which induce sections here. So I write splitting here. So as usual, we can take conjugation on this normal subgroup. Then we have a Galois representation in automorphism group of this. But before that, I also remark this pi1 geometric part has a naturally topological presentation generated by these standard generators and relations, and because of the comparison theory. So we have elliptic curve minus missing point 1. Then we have a tangent vector around here. Then I fix this as a base point of pi1. Then we have two loops, x1 and x2. And Z is just generator of inertia group. And I can work directly with this, but perhaps for later use, it's convenient to consider Pro-C version. C is usually full class of finite groups, but I only consider meta-abelian thing. So this is just an abbreviation of profinite or pro-L. L is a fixed prime, or pro-S. S is some set of prime numbers. This means just take to this one, replace pi to be pi of maximal Pro-C quotient of pi. And I just use the same notation for if once fixed the version. Yeah? But I don't change GK itself. So relative Pro-C version. Then obviously abelianization of pi is isomorphic to ZC. And this is a Procy completion of Z. And x1 bar and x2d is the image of the standard generator or generators of Procy theoretic Tate module of elliptic curves. And this is, I also write pi modulo commutator subgroup of pi prime. Commutator subgroup pi. Then the main subject is the action on pi prime over pi double prime. This is a second derived quotient of a second derived series. So second derived quotient. Okay, and the usual conjugation process, we have natural action of this first derived quotient, but also we can extend it to the action of complete group algebra over the pi up. Then Ihara's as in the Ihara situation, we know this module is this cyclic module generated by the image of Z. We have Z in this the image of Z in this second derived quotient. Okay. So so far we have in this situation from this splitting exact sequence we have representation of GK into automorphism of pi, but we are want to looking at double quotient. So extension of the first and second derived quotients. Okay. And but for convenience, I want to also introduce this mapping action on abelianization. This is just GL2 of ZC. And I write this matrix representation just low. So then what happens? So then I want to use this cyclic module structure to introduce one a core of this meta-abelian Galois representation. The idea dates back to 1984 letter of Spencer Block. Green. But unfortunately, this letter is unpublished, but and published introduced in Tsunogai's paper with a slight generalization in Mathematische Annalen, Nachrichten. 19 95. And in this, and here block proposed the analogous elliptic analog of of Ihara's construction. Which was in pi 1 of p1 minus 3 point. So I just want to introduce this thing very quickly. First, I introduced this notation k infinity to be the k together with adjoined by all coordinates of C power torsion points of elliptic curves. So this is just, of course, nothing but the kernel field of this law matrix representation. Then take elements of this G Galois group of k infinity. Then put the difference of the transforms of two generators, S1 and S2. Then, of course, now sigma is acting on trivially on abelianization. These two were inside the commutator subgroup. So one can evaluate these difference in second derived quotient. Yeah? So, but since we have here a standard generator and cyclic structure, so there exists Gi sigma in this commutative group ring such that Si sigma is isomorphic equivalent to Gi sigma dot Z bar in this second quotient. Yeah? For I equal 1 and 2.
Sorry. Yeah. When you say cyclic module, it's free?
Free, yeah, free cycling. So this is important. Yeah. So only one unique element can take. Then, on the other hand, we have standard relation. So commutator calculus works on. This is not very complicated, but I don't want to. Commutator calculus on this relation, we obtain consequent relation for this G1 and G2 in the following. I should write sigma. So this relation is very nice because x1 bar minus 1 and x2 bar minus 1 give mutually prime element of this group ring. So one can take a common factor of G1 and G2. So there exists sigma so this has to be divided by this one, and this has to be divided by this one. So we can subtract x1 bar minus 1, x2 bar minus 1 to give such unique element. And okay, so and this has a little fact. Is this is rather additive homomorphism, and also if sigma tau is gk infinity, and if taking conjugate, but conjugate can be taken in general element, then it looks like somehow like this. This can be easily derived from the definition. And here chi means a cyclotomic character, which is characterized by determinant of the matrix representation. So in some sense, he defined the additive representation of gk infinity to this group link. And also suggesting how one can describe this representation by using modular units also, which I worked out in a very little paper previously. So maybe here. This is already very old result of mine. Tokyo University Journal, 1995. Actually, epsilon sigma can be more detailed statement I will present later. So just very quickly describe by Kumma properties. These of some special value of theta function, or power roots of special values of theta function, and theta function is actually theta is something like this. Fundamental, so-called fundamental theta function. And the theta x is just theta of x1 tau 2 tau, and x equal t is inside. Okay. So this kind of power roots of special values were transformed by Galois actions, then which give rise to collections of Kumma characters, and it represents somehow each component of this two-variable power series. Okay. And but today's topic for continuing today's topic, I also introduced Tsunogai's efforts in his own paper, which kind of effort is as follows. Blocks construction we have such additive map. But this is adjoining all torsion points, so it's actually a little bit too big to deal with, somehow very imaginary Galois group. So he wants to extend this mapping from GK. Or, of course, you can modify this more quotient ring or somehow allowing denominators and so on. And then even in just some modification, extension will be very nice if possible. So he sorry. Yeah.
The previous statement, when you say it's described by Kummer properties, you mean the way sigma acts on these and truth?
Sorry.
When you say it can be described by Kummer properties,
Yeah.
you mean in terms of the sigma action on these.
In terms of sigma, yeah. So sigma acting on this, yeah. So restricting here is rather makes things easier because sigma doesn't change x itself. So each x gives one cycle. But if for general sigma x is going to sigma x prime, so and so it's rather delicate things appears. So Tsunogai's efforts how to do this.
But GK, when you add on pi divided by double commutators,
Yeah.
you should extend the references.
No, it's a different thing. Maybe you will see very soon. Yeah. Okay. So Tsunogai consider rho sigma to be ABCD. Yeah. Then, since we needed the elements inside the commutator subgroup, so this S1 sigma has to be written like this. Then the action on abelianization cancel out together, so inside pi prime. Then for this element, you gi the same way. But unfortunately, he derived very unfortunate equations for this gi, namely some very complicated polynomial in x1a to A, x1 to C, the B, x2 to B, C, and x2 to D appears. So if this right hand side is vanish, then one can extract the common factor from G1 and G2. But unfortunately, apparent observation shows this vanish only when ABCD is a unit matrix. So it means unit matrix means sigma is kernel of abelianization. So it's definitely this construction works only when sigma is inside GK infinity. Okay.
So, excuse me. So, but why is, maybe you're going to answer this later, why is it desirable to work in terms of E sigma instead of G sigma directly?
G sigma?
I mean, this thing makes sense only if you want the
but it fully depends on the choice of somehow generators, and and also it's not easy to track. So the goal, one of the goal is I want to describe if you want.
You want something like E sigma.
E sigma, E sigma, but somehow you are already had what will happen next section. So maybe you have very nice insight. But somehow E sigma is quite related with Eisenstein series. So, but G1 and G2 is rather indirect connections. Okay, so it's half time.
Sorry, well, I guess that's the formula you have up there.
Sorry?
The formula you have for E sigma up over there.
For here?
No, the previous thing. Those
Yeah.
can be used to give formulas for G sigma as well, right?
Here for sigma is inside the GK infinity.
For sigma in GK.
Yeah. But if you work GK infinity has no flow venues or such. So we want to descend the things to base field. This problem is rather a little bit same nature of my previous talk in August, computing functional equations of polylogarithms, periodic polylogarithms, without omitting lower degree terms. So somehow descending field of definition to as minimum as possible. So my approach today is the following. So, so one can construct certain mapping GK times DC to DC, which approximate E sigma on, if we restrict sigma to this small Galois group, like so I like this bold EM or maybe C also. E sigma is limit of m no yeah m and I don't explain the full details of each notations, but my mapping is constructed for each m in integers. So, inside C. And then this is actually not periodic in the second variable. But if you restrict sigma to this smaller Galois group, then it gives periodic in modulo, congruence modulo m, and then it gives you the element of finite group ring. Then we need to somehow modify constant term Kuma characters of discriminant, but enlarging the lattice m times. Okay. This is today's proposal.
Sorry, what is the last term did you say again? 1/12 rho.
Okay, so rho is okay, Kuma character. Kuma or cocycle. On
for delta
yes,
E.
yeah, roots of
For mth root, is that as it?
Yeah. So maybe you can take all power roots inside C. Then you have this thing.
Evaluated on sigma, is that what you mean? The value on sigma?
Yeah, sigma. Yeah, sorry. And if sigma is inside this group, then it turns out divisible by 12. So it gives constant somehow like this. Okay. So the time from
20 to 5, so we still have time.
25 until
20 minutes to 5.
until 25. Okay, so
20 to 5.
huh? 20 to 5.
Yes.
Still have
40
20
past
minutes,
4.
that's 40.
It's 40.
40 past 4.
You have another
Ah, okay.
25 minutes.
Okay. Sorry.
No, just 20.
Yeah, I start to, I think, yeah,
That's at 3:40.
3:40. Yeah.
Yes, yes.
Okay, so yeah, it's usual for me to exhaust the time. So my construction is as follows: somehow extending Tsunogai's approach, but more in a twisted way. Yeah. So I have UV and sigma is any element of GK, and UV is pair of GC, or maybe here. Then I consider generalizing Tsunogai's way. SUV sigma is x1u x2v transforming sigma, then x1 AU plus which one? dv, x2 cu plus dv inverse. Then it's inside pipeline. Yeah? Then I can evaluate this thing in the usual way. Coefficient of in the free cyclic module in second derived quotient. Then one crucial definition is my sigma uv is actually this GUV is inside inside this group ring. So no DC, yeah. This ring. So considered as a measure on this profinite space. So one can take modulo m concentration at the origin. So then so this then this gives you the integer profinite integer here. Okay. So perhaps before exhausting all times, I will like to show the main result, which gives somehow explicit formula for these values by using theta values. But somehow, as explained, we need to somehow technical so yeah. Yeah.
That's one question.
Yeah.
So there you define EM sigma UV.
Yeah.
So here, what is EM sigma in this one? This
What is EM sigma?
over here in this limit.
Limit.
In here.
This limit is.
What is that EM sigma?
Okay, so EM sigma. If sigma is inside here,
Right.
then it.
U and
yeah,
VR.
we have
U and VR.
periodicity. So you have a element of finite group ring. Then another limit to another direction. Yeah. Okay, so modular unit formula is describing the elements, but somehow we always have higher modulus. Modulo higher modulus, we obtain the explicit values. For this, for sigma and GV and M, and we want to conclude some modulo M square approximation of this value, and this the same as this Kuma character, but for general sigma, this itself may not guaranteed divisible by 12. So we need to some complement for, and this Kuma character has to be taken for a given UV. We have to take integer pairs, approximating enough to original UV, and also transformation after matrix transformation of this pair. Also, we assume enough approximation. And epsilon 0, 1 or 1, 3, 4, 12, depending on the whether the primes 2 or 3 or 6 involved in this story. So it's rather a very small detail. Then I define this Kuma character, which from this formula almost in suitable sense we can allow denominator 12, and then such values appears. And if you move all n, then this gives you the element of here. And then put together, then it gives you C-adic integer divisible by 12. Then finally, we obtain the approximation of this number. Okay, so a little bit. Yeah. So I have still have complicated. And just third section, I want to apply this purely group theoretical construction in in the situation of universal Weierstrass equation, namely y square equal but I want to consider this thing over a spectrum of Q of G2, G3 on delta. The space of all cubic equations with no multiple roots. Then this space is the same as the moduli space of elliptic curves with first differential, and also this regarded as a moduli space of such elliptic curve with distinguished sections other than the origin. Okay. Or this is just universal elliptic curve minus origin. Yeah. Then from here we have fundamental exact sequence of profinite fundamental groups in the same way. Okay. And here, but in this situation, we have very standard tangential base points in this space. Namely, we have Tate elliptic curves in the boundary. Not included. So somehow this rational power series ring gives you the standard tangential base points in this here. So I write here tangential base point determined by this Q. And also we have Weierstrass points. So from over this tangential base point, we also have Weierstrass tangential base point over Q bar. Yeah. Yeah. On the other hand, one can also interpret this space as a space of cubics without multiple zeros. Also, you can consider as a space of quartics. If you consider the quartic model of elliptic curve with one extra point, y square equal quartic gives you elliptic curve with two distinguished ordered points. And then the compatibility examination, one finds a very nice description of this mapping by Cardano-Ferrari resolvents of classical Galois theory. So I write Ferrari, Cardano. And this space of quartics and space of cubics is also interpreted as a braid configuration space. So we have, if you take a fundamental group of these spaces, we have such exact sequence. Braid group of 4 strings to braid groups to of 3 strings. Yeah? And this splitting is given by Tate elliptic curves. But also Ihara and Matsumoto construct standard tangential base points on these space of affine space minus discriminant locus. So it's one problem is how we should compare Ihara-Matsumoto's tangential base point in here and in here. And Ihara-Matsumoto's tangential base point gives you the GQ actions on braid groups in terms of Drinfield's formula of Grothendieck-Teichmüller groups. Okay. So this story is and the conclusion is like this. So comparison of Tate-White L-Strauss tangential base point and Ihara-Matsumoto's tangential base point.
Sorry, what are you referring to as Ihara-Matsumoto?
I didn't explain, but yeah, Ihara-Matsumoto's tangential base point is okay. So you have braid configuration space, so discriminants, yeah, such thing.
During the space
No, AM, yeah, AM. Yeah. Then you can consider somehow the image of such very special points, and consider the using this coordinates. You can you get the tangential base points valued in the Puiseux series in T. Yeah. So we have here. This is Ihara-Matsumoto's tangential base point, which gives you exactly the same as Drinfield's action on the GQ on profinite braid groups. Then in this situation, we have maybe this is almost obvious. This is a Tate-elliptic curve, and we have a Weierstrass type tangential base point, and also Ihara-Matsumoto's tangential base point. The difference is this direction is Q direction and T direction. Yeah? Q directions you have to extend vector 16 times, but T direction you have to shrink the vector to 1/16. Yeah? And this 16 and the alternative appearance of 16 is explained in this situation. This 16 is a principal coefficient of lambda functions. And this 1/16 is explained by somehow like this Jacobian elliptic curve, principal coefficient Jacobian elliptic curves and some scaling modifications. Okay. And also this kind of alternative appearance of 16 upper and lower alternatively is also observed in my collaboration with Leila Schnepp's concerning GQ actions on the higher genus mapping class groups. Okay. So 5 minutes.
It does not has nothing to do with the how you write the Weierstrass equation, and that is y squared equals 4x to the cube minus something.
Excuse me.
This 16
Yeah.
has nothing to do with the coefficient of x to the cube.
Nothing to do with x.
If you
Is it
change,
related?
Yeah. It's depends on the choice of the equation. So, yeah. Okay, so finally, and this geometric situation is also important to realize how one can take standard choice of generators of this for individual elliptic curves. So we have given an elliptic curve of a number field, then it fits in the modular space. Then you can connect the representing point to Tate elliptic curves by choosing one specific path in this moduli space. Then, but here Tate elliptic curves, we have a standard Frankampen patching of pi1 of p1 minus 3 points, which gives you standard generators x1, x2, and z in this family. So, if you choose one path in this modular space, then you can pick draw back the standard generators of Tate elliptic curves to specific elliptic curves. Okay. Yeah. So finally, I want to apply this theory to complex case, namely just over analytic situation. Then in this case, pi1 of m11 omega c is, as I explained, but discrete group of braid group, discrete braid group with 3 strands. But if you don't take profinite completion, it can be embedded into SL2Z and together with no rational integers. Here, usually you can take a sigma to ABCD, but actually I take a transpose of this one. And here we have a natural mapping from sigma to rho delta sigma. Delta is actually the discriminant, so representing permutation of 3 points in the cubic. Okay. Then B3 is in the discrete case. Fortunately, it faithfully represented by the pair of matrix and integer. Or sorry, rho is essentially the actually abelianization of B3. So we have B3 up is generated by tau1 standard generator. It's cyclic. But for some reason, I prefer to put denominator 12. Then the final result is we want to compute this my EM sigma UV in this discrete situation, which is actually the enjoyable formula, Rademacher-Ziegel formula, but or Dedekind sum formula for this case. Okay, so we have instead of GK, we have now a discrete braid group of 3 strands, and take UV. And in the approximation theorem, we had some modification. Maybe I should. We need to approximate the UV in approximate profinite integer to rational integers by taking a sufficiently big modulus. But in the discrete case, we don't need. So this approximation condition becomes empty. So we have exact number for describing this number. And after that, we can consider what happens in the monodromy actions on power roots of theta values. Theta value is actually 12th power of Ziegel units, and logarithm of Ziegel units is known as the product of generalized eta functions and Ziegel collection terms, and actually some very well famous work by Schoenberg and Glenn Stevens book, one can find such periodic matrix by using first and second periodic Bernoulli numbers. But we also need some correction terms. It's the coming from the difference of Ziegler units and Stevens generalized eta functions, and also some very small terms here. Then this is an integer value. We have for each uv we have integer. So if you form matrix, then infinite size integer matrix appears for each braid sigma, or but this generalized Radmacher function or this Ziegler collection terms has usually big denominators. But after that, these collection terms, then altogether you obtain integer value matrix.
So this E sigma UV is again defined in terms of sigma action on pi 1 modulo pi, the double commutator in the discrete case.
Yeah, in the discrete case.
So it's automatically.
Yeah, the same construction by group theoretical way. And this is essentially the period coming from logarithm of Ziegler units. So analytic number theory has an explicit formula. But somehow, if you work in a fundamental group, some path convention is very delicate, and some often plus minus mistakes. So it's not. It's rather complicated things to fix everything in an exact formula. Thank you very much.
Questions? Okay, so
It's really a theory for M11 and M12. Or
Sorry?
everything what we do here is M11 and M12.
Yeah. M11, yeah.
You can't-
So my talk is very elementary. No complex multiplications. So all elliptic curves with Weierstrass equations, you can specify this situation too.
So my question is, you can't do anything similar maybe in Genus 2.
Genus 2, I haven't investigated seriously.
other questions? I suggest maybe we have the discussion now for half an hour, and at 5:15 we have reception.